Hello everyone, good afternoon. Welcome to the class ECE341, the probability and stochastic process course. Today we keep working on the multiple random variables. Alright, and okay, so this week, this is the 10th week, right? This is for the 10th week. Monday's class is ECE341, and we will have midterm exam 2 at the 11th week Monday. Alright, there will be next Monday. And we will have a review and this week on the 10th Friday of 10th week. Alright, okay, and the coverage will be the part after the first midterm until this Wednesday. Alright, today's Monday, then tomorrow's tomorrow, right? Yeah, and okay, and Friday I give a review. All right. Okay, so today we keep working on the multiple random variables for multiple random variables. I will say x. In two-dimensional case, there will be just x and y. So maybe more, x1, x2, to some xn. Then we can have the joint. We have the joint density and the joint CDF, joint PMF, and of course we also have those for each one. So we have the CDF for each. So those are fxi of xi, which are the probability of xi smaller than xi, right? And we have joint one, that will be fx1, x2 until xn. Here's x1, x2, xn, capital N, or equal to the probability of x1 no more than lowercase x1, x2 no more than lowercase x2, until xn no more than lowercase xn. This is CDF. And we also have the mass function, the probability mass function PMF, similar for each one. For each xi, we have the mass function xi equal to lowercase xi, this probability, right? For I run from 1 to n. For I run from 1 to n. And for CDF, for joint one, we also have the joint one. This is one, and for this PMF, we also have the joint PMF, that is a P, the x1, x2 until xn. Here's x1, x2 until xn, or be the probability of x1 equal to lowercase x1, x2 equal to lowercase x2 until xn equal to lowercase xn. And this is the mass function. And we also have the CDF, the PDF for each one, each xi. We have a PDF, which is the derivative of, here's a xi, this is a capital F xi of xi. And for the joint one, that means the density function of all of those variables, x1, x2 until xn, and here's a lowercase x1, lowercase x2 until lowercase xn. This is we take derivative, partial derivative, right? Partial x1, partial x2 until partial x capital N. Here's CDF. Join the CDF. Join the CDF for all these x1 to xn. Okay, so this is a PDF. In previous classes, we just suppose we have two random variables, right? That means capital N is 2. But actually, you can have these. It's not hard, just longer. When you write, you need to put more terms for each definition. All right, and we also have those numbers. We have those average. We have expectation value for each xi. We have the variance for each xi. Okay, this is for single one. And of course, if you want, you can also have xi, the standard deviation, sigma xi, which is the square root of the variance. Right, we can have these for all the i's. And then we can have the joint one, right? We have more than two random variables. So here we have the two numbers. One is a covariance of xi and xj, which is the expectation of xi minus exi times xj minus exj, and this is a covariance of x1 and x2. This is a definition. Writing this way is a definition, but we can have a formula to calculate it. This formula is simpler than definition. It is expectation value of xi times xj minus exi times exj. So this is a formula. Now when you do calculation, you can use this one to do the calculation. Right? And we also have this is covariance, right? Let me write down covariance. And we also have another number, is r xi xj. Sometimes write as r xi xj or r xi xj. Okay, this one equal to just the expectation value of xi times xj. Alright, this is a correlation. This is correlation. Alright. Correlation. And let me see, we need another. Okay, we have another one, which is a rho xi xj, which is a covariance of xi and xj over square root of variance of xi and square root of variance of xj. Yes, the square root. This is just standard deviation, so this is sigma xi times sigma xj in the denominator. Numerator is the same thing. Alright, so this one is called as a correlation coefficients. COEFFI. Coefficient. Yes, the name is similar with this. This is correlation. This is correlation coefficient. The name is sometimes confused because they contain the same part. But the name of this row is longer. You need another word, the coefficient. So this is a correlation coefficient. This is just correlation. They are different. Okay, there are some average values. Then we can have some, we have, when we do the calculation, we have some formula. Okay, we already have this formula. We can have something else, some form of, we need some definition firstly. Definition. Okay, first one we already have, this is independent, right? We say independent. X, Y, two random variables, they are independent. This related with this one. The first one is if the joint CDF of X and Y equal to the multiplication of X of X times Fy of Y. It is also equivalent with the PDF. If we have PDF, this is for continuous type, right? Fx, Fy. Or we can have a formula for this is for the discrete type. It's joint Pxy, X and Y are equal to Px of X, Py of Y. So we call this independent. And we have another concept is we call X and Y. They are orthogonal. Orthogonal. G-O-N-A-L. Orthogonal. If R, X, Y equal to 0. This is this one, correlation. If the correlation is 0, so we call X and Y, they are orthogonal. And we call X and Y, they are this is uncorrelated. If and only if the covariance of X and Y, they are 0. It is 0. The covariance is 0, and this is as same as the case. The correlation coefficient rho xy is 0. This is uncorrelated. Okay, we have these three, and then we can have some formula. We need this one. We have some formulas. The expectation value when we have X and Y, if we combine these two, here A, B are constant, X, Y are random variables, right? X, Y, they are random variables, and A and B, they are just numbers. They are not random variables. Alright. Then this one will equal to A of E of X plus B E of Y. We have this. And then for the variance, okay, I separate these by two parts. For variance, I have AX, the variance will equal to A squared times the variance of X. Alright, so here you times A. You move it out, you need to put a square here. Okay, for variance. And for sigma, the standard deviation of AX, this will be absolute value of A times sigma X. Alright, this is for variance. And this is for A times the random variable, the variance of this case. And another thing is for summation, the variance of X plus Y it will equal to variance of x plus variance of y plus 2 of covariance of x and y. And this one will equal to, if x, y, they are independent or uncorrelated. I say uncorrelated. Uncorrelated, the covariance is 0, right? Uncorrelated. So this part is 0. And we have this simpler formula. It's variance of x plus variance of y. Alright, so we have some formulas. They might be used for when we want to do some calculation. Okay. Then, alright, let's consider some example. Check some example. We consider x, y. They are two random variables with a joint PDF probability density function. It is f x y of x and y are equal to some constant k or 0. In which case is constant k? In the case I use if absolute value of x plus absolute value of y smaller than might be equal to 1, and otherwise. This one, absolute value of x plus absolute value of y no more than 1, it will be an area like this. Is this part. Here's 1, here's 1, here's a negative 1, here's a negative 1. Then every element inside in this, this is a rectangle, right? In this rectangle, then x plus y, no more than 1, right? No more than 1. Or absolute value of x and y, do summation. There were some value, no more than 1, right? You pick any point in this area. You can check x plus y. X plus y were smaller than 1. So this area, in this area, the density function has a non-zero value k, and when the outside this area, the PDF has 0 as a value. Okay. Then we want to do something. We want find the k. Second thing, we want to find, we can have fx of x, fy of y, and the third one we want to have ex, ey, variance of x, variance of y, and the covariance of x and y, and the row of x, y. We want to find all of these. Okay, how to do it? Alright, for the first one, we want to find k. So we use this one. We know the integral from negative to positive infinity, the density function. This will be 1. Now we know this, right? The totally probability, overall probability is 100%. We have this. Then we need to do the integral in this area. Under this area, I say this area, I just use S to represent this area. Alright, it's kind of a sample space. So this is this one, x and y belong to S, and here's a k and the dx dy. Right, we have these. Then this one will be the volume under this area. Right, you can think like this. You have this part. This is S. This is S, right? Here's 1, 1, negative 1, negative 1, okay, like this. This is X, this is Y. And we do integral with some constant K here, right? Okay. Some value K here. So this is K. Then the integral will be the volume of this part. Okay. Here's K. And the area of this rectangle, it is what it is. I put this one. So this is 1 by 1. This is 1, right? So here is half of 1. Half of. I have 4 of half. So totally 2. This area is 2. So this one equal to 1 give us 2 times K equal to 1. So we have K is 1. Yeah. Okay. I do the integral by this way based on this graph. I can have it very easy. You can also step by step. You plug in, you do the integral, and the final answer should be same. All right. So K is 1 over 2. All right. So we have K. We have K. The second one we do want to find fx and fy. Forget this. The fourth. Check the independent, whether it is independent or orthogonal or uncorrelated. Right, we want to find this. Okay. Then the second part, I want to find fx and fy. Then what it is, fx of x, there will be integral of fxy of xy. Here's a dy, and y run from negative to positive infinity. This is a marginal distribution, right? Marginal density function. I want to know the marginal density function. We have the joint density function. I want a function of x, so we do integral to remove y. Alright, and this one, y will run from, okay, y, where will be y? You can see. Okay, this one, this is x. For every x, what will be y? For every x, what will be y? Y will be run from here to here, right? But at this place, no y. So actually we have two cases. It will be 0 if x larger than 1. Larger than 1 or smaller than negative 1. So absolute value of x larger than 1, in these two parts, the density is just 0. Density is 0. And when absolute value of x smaller than 1, is this part. Then we have the integral will run from this point to this point, right? This point to this point. So it will be 1 minus absolute value of x. Another one is what is this value? This one is x plus y equal to 1. So x is fixed. Y will be 1 minus x. So this is 1 minus absolute value of x. This point, right? This is 1 minus, and this is opposite with that. So it's negative 1 plus absolute value of x, right? Okay, and here's a k. K we know is 1/2, and here's a dy. All right, and this will be it is 0 if absolute value x is larger than 1 and maybe equal, right? And this one do integral, I have half of y, and y will run from negative 1 plus absolute value of x to positive 1 minus absolute value of x. So here's if absolute value is smaller than 1. then this will be, okay, still two part, 0 if x larger than 1, absolute value of x larger than 1, and this is a 1/2 times this one minus this one, so it's 1 minus absolute value of x minus 1 plus absolute value of x if x smaller than 1. Okay, let me do some simplify. This is 0, I keep it, and this is 1 minus 1, they cancel, and then it is negative minus x. I got something wrong? Oh, here's a negative 1, sorry, I forget this, it's a negative 1. Yeah, so this is 1 minus a negative 1, I have 2, and then minus absolute value x minus another absolute value of x, so minus 2 of absolute value of x if x smaller than 1. Okay, now I have it. I put the non-zero value in first, so this part in the first, but the 1/2 can be cancelled with this 2 and the 2, so it is 1 minus absolute value of x if absolute value of x is smaller than 1, and it is 0 if absolute value of x is larger than or equal to 0. Alright, so we have the marginal distribution, this PDF of x is this one, so fx of x equal to this one. Alright, then similar we can have fy of y or equal to 1 minus absolute value of y if y absolute value is smaller than 1, and 0 if y absolute value larger than 0. We will have this, and we can have the graph of these two functions. It will be looks like this. This is x, here will be, when x is 0 it is 1, negative 1, this is 1. This is for x, PDF of x, and for y it is a similar thing. This is y, here's 1, here's negative 1, here's 1. Okay, so we have the marginal distribution, the density function, probability density function. Right. Okay, this is the second part. Then the third part, okay, we want to find all of these numbers. Third part, the EX. Okay, to calculate EX, we have two ways now. We can use the integral of x times the density function of both x and y. Here's a dx dy. We can use this. We can use this, or we use just one. This is x times fx of x dx from negative to positive infinity. We can use both. The result should be same. Okay, so now let me use this one because I already have the function, right? I have this function. Right? So I can just use it. Oh, this is I have an absolute value. So for positive x, this is a positive. For negative x, I need to put a negative in front of it. So I use this. I will have the integral for this is 1. Sorry. For x larger than 1, this is 0. Right? Larger than 1, this is 0. So we don't need. We only need x no more than 1. Absolute value of x no more than 1. So this is from negative 1 to positive 1. But I separate for negative x and positive x. So negative 1 to 0, and the other integral will be from 0 to 1. Right? Okay, since negative 1 to 0, and the x times density function now is 1 minus negative x, because x is smaller than 1, negative value, so absolute value will be negative x, right? Okay, this is the first part. And second part, from 0 to positive 1, this is x times the density function now is 1 minus positive x, dx. Okay, so this one gave us integral, here's x plus x squared dx, and this integral, this is x minus x squared dx. Okay, so this is x squared over 2 plus x cubed over 3 from -1 to 0, plus this is x squared over 2 minus x cubed over 3 from 0 to 1. Okay, now let's plug in 0, I get 0, and minus plug -1, I have 1 over 2 minus 1 over 3, and here's a plus. When x is 1, I have 1 over 2 minus 1 over 3, and when it is 0, it is just 0, right? Okay, what it is? It's still 0, got it? This is -1/2, positive 1/2 is 0, and here's a positive 1/3, and this is negative 1/3, so cancel, right? This is 0. Okay, we have EX is 0. And similar, you can have EY similar. This will also be 0. All right. Then we check the variance of x. Variance of x equal to E of xy minus EXEY. But now this is 0, this is also 0, right? We just got it. EY is 0, and also EX is 0. So this is just the E of, oh, sorry, I confused. Okay, this is a covariance. That's right, sorry. So variance of x will be E of x squared minus EX squared. Okay, and then EX squared, there will be the integral of x squared times fx of x dx minus EX is 0, so 0 squared. That's nothing, right? Okay, this integral, now I separate it from -1 to 0. Here's x squared times 1 plus x, right? This is 1 minus absolute value of x dx, and plus from 0 to 1, it will be x squared times 1 minus x dx. Okay, so this is integral of x squared plus x cubed dx from -1 to 0, and here's a 0 to 1, integral is x squared minus x cubed dx. Alright, so this is x cubed over 3 plus x fourth over 4, and x run from -1 to 0, and plus this is x cubed over 3 minus x fourth over 4, and x run from 0 to 1. Okay, when it is 0, it is just 0. Then minus x is -1, -1 cubed is -1, and over 3, and plus -1 to the 4th, it is +1 over 4, and plus this one, I plug in 1 in, I have 1 over 3 minus 1 over 4, and subtract, okay, x is 0, it's just 0, right? Alright, this is 0, 0, cancel. I have negative 1/3, so this is a positive 1/3, and positive 1/3, so 2/3. and negative 1/4, another negative 1/4, so negative 2/4. So this is what? This is a 2/3 minus half. So this is a 6. Here's I times 2 times 6, right? So here's a 4, and the minus I need times 3 here. Okay, so this is 1/6. I have variance of x is 1/6, and similar we have variance of y. It is also 1/6. It is also 1/6. All right. Then we check the correlation, covariance, and the correlation coefficients. Right. For covariance, this one we need the formula E of xy minus Ex times Ey. But this part, it is 0. So this is just Exy. It is Exy. Ex times y. This is not this, times y. Alright. And this equal to the integral of x times y and f xy dx dy. Alright, we have this one. Here you have to use the joint density because you need both x and y. This is okay. Then the integral, we have this area, right? This is x plus y absolute value equal to 1. This is a bound. This is bound. And the inside is smaller than 1. Outside is larger than 1. For the inside is smaller than 1 part, I do the integral. So x will run from, this is negative 1, this is 1. So x will run from negative 1 to 1. And for every x, y will run from here to here. And this is a negative 1 plus absolute value of x, and this one is 1 minus absolute value of x. Okay, so it will be integral x run from negative 1 to 1. And for every x, the y will run from negative 1 plus absolute value of x to 1 minus absolute value of x, and the inside is x times y. This density, now we know it is k, that k is 1/2, right? And then dx dy. Okay, so this one will equal to negative 1. I copy it. I do the integral of this part firstly. X and this 1/2, you can think they are constant for this integral, right? This integral for y now it will be y squared over 2, and y will run from negative 1 plus x absolute value to 1 minus absolute value of x dx. So this is okay at 1/4. I put it in the front. And then here's the integral from negative 1 to 1. It is x times this part. This part is 1 minus absolute value of x squared, right? This is y squared. This is squared, and the minus negative 1 plus absolute value of x squared dx. Oh, it's 0, right? These two are same. It's square and square. Okay, it is 0. 0 times x integral, which is 0. Okay, we have the covariance is 0. Covariance is 0. And actually it is this one, right? This is the Exy because this part is 0. So Rxy, the correlation, it is also 0. It is also 0. Well, we already have it. And also the correlation coefficient, which is the covariance of x and y divided by the standard deviation of x and the standard deviation of y, this is also 0. Okay, so now we have these for the we finish the third part, right? With third part, and the fourth part we want ask for whether these two random variables x and y, whether they are independent, whether they are uncorrelated, or whether they are orthogonal. Okay, now the answer is x, y, they are not independent. Because the density function, the joint density function, do not equal to the multiplication of this marginal density function. They are not same, right? This one is, it is a constant. This will be k or 0. And these two, the function looks like this, right? Both x, y looks like this. You multiply these two together, it will not be a constant k or 0. This is k or 0. It is in this area. In this area, it will be a constant, right? You have a constant k, a constant 1/2. So you times these two, you cannot get that one. So they are different. They are different, so they are not independent, right? And then we have r, x, y equal to 0, so x and y, they are orthogonal. They are orthogonal. And also the covariance of x and y equal to 0. So we say x and y, they are uncorrelated. Yeah, uncorrelated. Okay. Yeah. Actually, this is a kind of example. We generally we have these. We have a kind of let's say theorem. Okay. So if x, y, they are independent. They are independent. Then we can have the result is we can have these. We can have x and y, they are uncorrelated. Uncorrelated. Alright. And uncorrelated, we can also have the result like now we have a formula, right? We have that formula, remember? For uncorrelated, I listed some formula here. I have formulas joint. Here we have this part. We have this one, you see. We have this one. If they are uncorrelated, then it is this one, because this part is 0. Right? We have this formula. Alright. Yeah, I already have it. Okay, so here I just put it this one. From here we can have this one. But this way, usually you cannot show. You need more information. You just know x, y uncorrelated. You cannot say they are independent. But they might be independent. But not always, right? And the example we just calculate this, give us an example. This one, they are not independent, right? They are not independent, but they are uncorrelated. So uncorrelated, but not independent, right? So this is the example. This is one example. You cannot go from this statement to previous statement. All right. Okay. So this is one example. We can have those coefficients, and we also have this relation between independent and uncorrelated. Okay, that's what we all for today, and see you next time. Bye bye.